Hi, my name is Salase Dumenu, and my partner is Andres Cordova, and this is our presentation 4 for ENGI 460, and today we're going to be talking about the general methods for generating random variates. Alright, so a quick overview here. We're first going to look at the inversion of the CDF, or the cumulative distribution function, and then we're going to take a look at envelope rejection, and then also tackle ratio of uniforms method. Okay, so first we're going to look at the inversion of the CDF. So basically, if x is a continuous random variable with cumulative distribution function f, and r is u 0 to 1, then we'll assume that the random variable f inverse of r has a cumulative distribution function that is basically equal to f, or the same as f. And then we're going to use this example below and say that, so if p in parentheses f inverse of r is less than or equal to x on support from 0 to x, and over here we're just going to let x denote any real value belonging to the support of f. And then, this is basic math, so you see that another way to write the f inverse of r is basically r over f, and we say that is still less than or equal to x. And then once we take the f over, it becomes r is less than or equal to f of x, and then the range, as we've been given, is from 0. We know that r is within 0 and f of x, and since we know that we're going from 0 to x, we can basically assume that f of x is the given result. Then we're going to go over to MATLAB to look at another example of how this can be written in MATLAB and what our inversion would be, or what it will look like. But for the one in MATLAB, we're basically going to look at the exponential distribution. Alright, so now that we're in MATLAB, this is a very simple code, but I'm going to run through real quickly and then tell you what we're trying to do here. So as you can see, it's commented at the top. It's an inversion of the exponential CDF, and then this is basically our input that lets us refresh every time we try and run it. It's a simple integration, really. We're gonna find sims of x lambda r, and then our equation is the exponential distribution, which is I. We're naming that I, and we're gonna say it's equal to the integral lambda times the exponent of negative lambda times x, and that is going to go from 0 to x. And then once we find out what I is, we're going to solve r. We're going to try and find r using the I that we found, and then we're just going to subtract that from 1. So basically we're going to solve for r 1 minus I of x. So I'm going to go ahead and run this. So we expect to get our I, and then we expect to get our inversion after we run this. Yeah, so as you can see in the results, the command window, our I is 1 minus the exponent of negative lambda times x, and then when we subtract that to find our r of x, when we subtract that, the answer we get is the negative log of r over lambda, which is what you would get if you solve this mathematically. So that is basically how we find the inversion of the exponential CDF using MATLAB. So next we're going to look at envelope rejection, and that is also known as the accept reject method. And the main idea with this method is basically to try and alter the relative frequency distribution of y values using the probabilistic rejection step, such that the accepted ones, or the accepted y values, have precisely the required distribution f. And then normally the accept or reject is based on where the point falls on the density graph. An example in MATLAB should better explain, the graph should better explain how this works or what it looks like, and we'll be doing that in the next slide. But a good, not necessarily reason, but a good indicator to employ this method will be usually when the inverse CDF cannot be computed, or if it's hard to compute. and also when the f of x can be evaluated at least up to a normalizing constant. Alright, so now in MATLAB we're going to try and create the envelope projection for a folded normal density with an exponential proposal density. So this is the whole code. This is our function code here. We have 3 functions in here, but I'm going to try and touch on the important parts of the code, and then we'll run it, and then we can talk more based on the graph that it's going to generate. So we have our function, which is our first function, which is the x val, and then our second function deals with our c and then c equation, and then the third one is just basically our z function. So in our x val, we set our lower and upper bounds 0 to 7, and our c, we want our x to run from 0 to 20 increments of 0.01. We have our constraints here, and then we have set our c, which is basically taking I believe it's our h of x, it's subtracting our h of x from our g, or basically our h of x from our g of x, and then our c equation must be equal to, it's just equal to constraints. So in our function z, this is basically the most important part of the code, basically in my opinion. We have set our g, which is equal to lambda times x, negative lambda times x. H is equal to 1 over the square root of 2.4 pi times the exponent of negative lambda times x squared over 2. And then this is our z here, which is going to be the sum of g minus the sum of h. And then we want to plot that finally. And this is our plot function here, which is saying that our x, which is from 0 to 20, letting our lambda equal x of 1. We're going to plot x, which is plot our g of x first, and then we'll hold and then plot our h of x for that. Alright, so I'm going to go ahead and then run this code and then see what the graph gives us, and then talk more from there. Alright, so let me go ahead and expand this. So first we see our g of x, which is our blue slash line, and then our h of x, which is our solid red line. So basically when we look at the graph, we can see how the function g measurizes h, and then we usually say that the graph g envelopes that of h when the two functions are equal at one or more points, and I guess we can see that somewhere here. So based on this, we can say that the function g envelopes h, and then this will basically generate a variate from a density proportional to h. Alright, so lastly we're going to look at the ratio of uniformness method. So if we suppose that there are two independent uniformly distributed random variables, u, which is one of them, which is from 0 to 1, and then v, which is u negative a to a, where a is a known positive constant. What we can basically do with this is we can create a new variable x, as you can see in the green box below, and then equate that basically v over u, and then when we make v the subject, that basically becomes x times u. What we already know is that the joint density of u and v is 1 over 2a, and this is over here. So what we're going to try and do now is find the joint density for u and x, so u and the new variable that we created. And basically so now this is going to be the function for ux, and that is going to be equal to f, subscript x bar u, and that is going to be equal to u of xu times f of u. And basically what happens is the partial derivative of v over the partial derivative of x times v subscript v bar u, that is going to be equal to u. And what you see here is that this v now becomes our xu, because we're switching and putting that in here. So that becomes our xu of u of fu. So next, our function basically becomes our u. We take our u, we put our u in front, and that becomes our u times the f subscript uv of u comma xu, and that is going to be equal to u over 2a. So the joint density for u and x is going to be equal to u over 2a. And this is going to be over the support of negative a to a for xu. Remember that is no longer v because we switch that out. And 0 to 1 for u.